Well, maybe it's not comments, but I directly need not everything. Some of them are still like more notes.
Oh, and then my talk was really
and you think sometimes, sorry, the problem.
More coffee?
Yeah, sure. Yeah, I'm going to office.
No, that was fine.
Yeah. I did it this morning because I thought I'm but I thought we have one additional week, so I may fix the errors and run the experiment again, and we can somehow.
She always busy. Good supervision.
No, they haven't announced anything. The deadline is up. The interesting thing was Miguel, there was like people are going to sub through the day.
Yeah, you really see that.
Yeah.
It's quite a bit better now, but it was quite terrible then.
There should be loads of submissions.
Yeah.
Really?
Yeah. Maybe more than a couple.
So,
yeah, that's why I'm expecting more.
We just contact
what to do.
Did you also, I asked him to check the applicants. I don't know how good it's going to be, but he said everything is fine, but there's the proof.
Yeah,
you get the money for the train from down.
Yeah, but we don't have proof.
So,
just saying that.
So,
yeah, you get electricity from more
Yes. We should say that, yes. All right.
Yeah, no, I can really sound because I don't know my phone.
You know what? No. Sit down and click that. Sure. On my device.
How about this? I haven't seen it. I'd like to go to It's not the smooth side.
Don't you have the application?
Because in my case, it is also the account. Pretty often.
we get quite heavy
Oh,
on
it's that moment card.
I thought you weren't coming.
You are somewhere in the middle. You are somewhere in the middle.
say it's Roman, because Roman was...
Well, he's done now, and he's only left, so
Yeah,
he's only left.
No, Roman is more profound. I would say from University of Manchester that is more complex.
Oh, yeah, I can see it.
As many people inside.
You know exactly what's going to happen.
On the floor. I've seen
Mine's absolutely fine, okay.
a bit beaten.
But it's also, no, this left much better. You're kidding. Also then,
No, I've seen it before.
the Westminster happening twice. Yeah, it's beautiful. Today.
So welcome to the very last session, constraint solving. And our first speaker is a local, just came out of the Nightingale and straight into a PhD under the supervision of Karen Petrie. So his name is Xu Hu. I hope I got that reasonably okay. And he's going to talk about tuning constraint solvers using genetic algorithms.
Hello everyone, my name is Xu Hu. I'm a PhD student in Dundee University. I'm supervised by Dr. Karen Petrie and Dr. Keith Edwards. And today my talk is about a sexual genetic algorithm based system for automatically tuning constraint satisfaction problems. First one, what is the sexual GA? Sexual GA different with the standard GA because sexual GA use a different and two selection strategies in the same time. So why is sexual GA? The efficiency choose of the preprocessing levels can highly reduce the searching times. And sexual GA can help the researcher to find the right and correct parameter settings. And it's better than the standard GA. And in the last, in the next experiment result, we will show it for us. So before we deep explore the sexual GA efficiency, we will introduce some basic definitions. The first one is constraint satisfaction problems. So what is the constraint satisfaction problems? Usually it's a three-part. First one is a finite set of variables. So the problems have a set of finite set of variables, and each variable have a finite set of domains. And then between each variable, there is a relationship. We also can say it's a constraint to restrict each variable. So usually it consists of about three parts. And maybe it's not easy to understand, and there's a simple example here. We will use a Stuku to show how this constraint satisfaction problems. Here is the Stuku. So everybody knows Stuku? Okay, so I didn't take time to explain how it works. So Stuku in here, and we can see first three squared first. In commonly, the computer to solve these problems, they just use to list all the combination for these problems. So 1, 2, 3, 4, 5, 6, 7, and every grid, each grid we have such a variable range. But how constraint satisfaction programming to serve this one? You can see the first call 3 and 3 grid, and we can see 3, 4, 7, 6, 8 there. So another 4 blank one. We can delete the search space to 1, 2, 5, 9. And then we can use another constraint in the definitions. We can see the first line, and there's 1, 2, 3, 4, 6, 7, 8 there. So it means 2 and it means 5 and 9. It should be blank 1. And then we can see another 2 lines on the second lines and the third line here. The nice here, nice here. From the definition of the tuple, each lines, each column, the number from 1 to 9 just appear once only. So it means here, here. And here, oh, sorry. So here, just 5 is we can find, because 9 can't appear.
That's not right. But
Oh, sorry, it's a 9 there. Sorry, it's 9 there. I didn't check it, sorry. So how, sorry, that's a bad example. Sorry. So how to serve this constraint satisfaction? We usually use constraint server. Here in our experiment, we use server is called Minion. Minion is produced in Los Angeles in 2007, and he's a free and open source server, and he's one of the most efficiency server in the world as well. This is the reason we use it, and there's some tuning flag inside. We want to tune it by the genetic algorithm. So here is some. Check the result is correct or not. And preprocessing. So which preprocessing we need to choose before we start searching. And vary order. So what's the order's variable, or what kind of variable order we need to choose? From small to large, large to small? Okay, so we are back to talk about this genetic algorithm. How genetic algorithm is and how they were used to select for the satisfaction, the constraint satisfaction problems. Here, we'll first talk about the definition of the genetic algorithm. So, genetic algorithm is come from the Darwin's evolutionary theory. But it's proposed by Joe Holland and his colleague in 1970. And in a standard GA, there's 3 basic things inside. The selection. So what kind of parents we can choose? And usually, roulette wheel selections we'll choose as the selection strategy. And crossover. And we'll select the right parents and cross them and mating them and exchange the information. And mutation is just allow every individual chromosome have the chance to improve fitness. So what's the sexual genetic algorithm? It's more like the nature behavior. In the nature, the male group, or the good fitness group, they always want to have the chance to get a shot. The chance, they want to pass his good fitness for the next generation. And the female group, they have all have the equal chance to generate the next generation. So it's, this concept is from the nature behavior. So in sexual genetic algorithm, there's two groups as we talk. There's a male group, we also can call it competitive group. So each chromosome, they will compete and to win the chance to generate the next generation. And the female group, and each chromosome have each chance to generate next generation. And another concept there in the sexual genetic algorithm is elitism. So we will allow some percentage of the good chromosome from the male group. So we call them is elitism in here. So here is some flow chart about how it works. We can from this chart to see the sexual genetic algorithm. We are studying and initial some random generation population, and then they will random mark which one is male, which one is female, and then the female one they will all get the same possibility, and male one will select some good and crossover and mutation, and then we will evaluate if this result is good or not. To improve the efficiency of the SexGA, and I apply this one to solve the TSP problems. TSP problem is job salesman problems. It's a classic problems. TSP problem is in N cities. So we want to find the shortest path, and this path, the route can pass each city once and only once. And here is the result, how the SexGA works. And you can see there is 4 lines. The blue lines is standard GA, and the top 2 is, the red one is, the top 2 is with the elitism percentage, but with a different percentage. And the yellow one is used very bad one, and we call it's a roulette wheel selection to choose the percentage. And then after this one, we apply the sexual genetic algorithm to solve two constraint satisfaction problems. One is BIVD, one is Lawford. And from this table, we also can see, and the sexual GA is better than standard GA as well. Conclusion, from 2 experiments we can see, and we can show some results. First one, sexual genetic algorithm is a more efficiency than the standard GA in this paper. Another one is properly elitism percentage in sexual genetic algorithm can lead a good result and better result. So future work. In the next step, and we will do 3 things. First one is we will try use SexGA to apply more constraint satisfaction problems. And second task, because the sensibility of the parameters of the genetic algorithm is hard to control as well. And so we will explore this area as well. And last one, because I do another research on self-learning genetic algorithm, so how about the efficiency to combine these two, and so we will do this such exploration as well. And then that's all. 15 minutes.
Any questions?
Yeah, in the different graphs that you showed, the sexual GA in one version did worse, or was the worst of all four. So,
So which one?
we had these four graphs, yeah?
Yeah.
And then you had the yellow one, which was the sexual GA with roulette.
Okay.
Yeah?
Which one's the final?
Just 1 second. Presentation, I think. Yeah, that one. Okay.
Yeah?
So this one, right?
Yes.
So
And you had the yellow one was sexual GA with roulette.
yeah,
It's
it's
worse.
worse than.
Yeah. So in some sense, I was not sure about your one conclusion where you said, without any proviso, sexual GA is better than standard GA. That seems to speak against this picture there.
Oh,
yeah?
what
So
I mean
you can equally say it is worse than standard GA from that picture. So I can, take the opposite position, and the data that you have derived would also support that.
Yeah, yeah. What I mean in my conclusion is such GA, yeah, is more efficiency than standard GA. I always see nothing, but properly, it isn't percentage is very important. If set here. If you use the wrong percentage where this works, that's what I mean. It's not the opposite conclusion. What I said is you can, if you use the right percentage of the reason, that's definitely the good one. And if you use different or you use not right one, and definitely you can't find the right answer.
Yes, but that may be due then also to that specific kind of method that you use. When you fine-tune them, then also you may get with standard GA much better results. So all I want to say, it is not that easy to draw general conclusions from the data that you have, and you have to be slightly careful.
Okay. Got it.
Yeah.
Yes. Okay.
Thank you.
On this graph, how do you measure fitness?
Fitness. The fitness is in this one is TSP problems, and the TSP problems are just too easy to make the fitness, and the fitness is just one because it's just in a cycle, and then there's the fitness, and one is the best one if it's just in a run.
So it's the distance from the optimal solution?
Sorry?
It's the distance from the optimal TSP solution?
Yeah.
No.
Any further questions?
And what are the parameters you are doing? It's just the three, or how large is the vector that you
For
are
the TSP?
doing? Yeah.
The TSP, we choose here is 30 cities problems.
Oh,
I'd just like to ask one thing. So with a kind of local search type of approach, like a genetic algorithm, it's good to, you need to balance diversity with coming in on a good solution, right? So does this allow you to do that? Is there some parameter that allows you to either press more towards the good solutions or diversify more? Like the number of elites or something like this?
Sorry, could you say that again?
Is there a parameter that you can tune on your sexual genetic algorithm that allows you to either push more towards good solutions greedily Or if you tune it the other way to diversify more. That's all I'm asking.
In here is tuning. I just try to find the best one, and if possible, and that's the result I can find and compare if I use the standard GA and what it is, and that is here. And if I'm not sure about how this answer your question.
All right, I'm not worried. Okay, let's thank our speaker again. Judge from the University of Strathclyde, you probably met him already, and he's going to tell about their work on a new heuristic for constraint solving for AI planning.
Thanks very much. Good afternoon. I know everybody's tired, so I'll try and keep it reasonably short. As Peter says, it's a CSP heuristic for AI planning. So what I thought I'd do is just very briefly introduce AI planning in case you don't know what the heck it is. Then talk about using CSPs for planning, and then the CSP heuristic that we're going to use, and some early results that we've got. So first off, if you're going to trip or do anything essentially, let's say a trip, you're going to think about mode of transport, you're going to think about what you're going to wear, you're going to think about when, you're going to think about what route you're going to take. Essentially, you're going to have a list of things, a list of actions to achieve your goal, a plan, right? In AI planning, we attempt to automate that. So obviously, it's a type of problem solving where we start with a defined initial state. We have a set of actions which can change the states, and we're aiming to arrive at a goal state. So obviously when we start out modelling the real world, we're going to have to get rid of quite a lot of detail or we'd be overwhelmed. So in something called classical planning, we assume a finite and fully observable state space. The only thing that can change the states are these actions. There's nothing that can come from outside that world, so there are no events that can do anything apart from those actions. The actions don't take time to carry out, they're instantaneous, and if we know the state before the action, we know the state after the action. There are types of planning where that's not the case, but we're dealing with classical planning, so it's fairly controlled. Through the years, there have been various representations, some more expressive than others, starting with situation calculus, going through something called strips, which was both a schema and the name of an algorithm, which was used in one of the early planners, I think in the 60s, so probably before many people were born, into something called ADL, which was a bit more expressive. So the research community's now come round to using something called PDDL, which is the planning domain definition language. So when you're describing a problem, just for example, this one, we use two files. A domain file, which is a kind of general description of the world or the domain that we're talking about, and an instance file. So, as we see here, the domain file describes the predicates and the actions. In a world like this, a very simple example, obviously, it would be something like drive the truck, board the truck, load the package, general uninstantiated actions. The instance file has a load of objects which describe the world exactly, and as I say, will describe all of the objects in that world. So, just a quick example of a domain file. So we're just setting up things. We've got the predicates up here. This is just one. Oh, so it isn't. Oh. Thanks a lot. So we've just got one action. Obviously there's going to be many actions, but I can't fit them on the screen. So this is just a load truck action. And got the objects here. Precondition of this action is that the truck is in a given location. The object to be loaded in the truck is in the same location. The effect of that action having been carried out is that the object is no longer in the location and the object is in the truck. And as I said, there'll be many actions like that described. So the instance file sets up all of the objects, describes the initial state, which is the black text on this diagram. So driver 1 and 2 and truck 1 are at S0. Incidentally, the drivers can walk on the thin lines and the trucks drive on the thick lines. So yeah, that's the initial state, sets up the world, and oh, it's too late, I'm falling asleep. Going the wrong way. Sorry about that. Okay. So yeah, setting up the goal state. So the goal state described in red on this. So pretty obvious what's happening. So when we ground out something like that problem for any kind of interesting problem, obviously it starts to become really pretty big and becomes intractable. And what they normally do in planning is build a dedicated kind of bespoke system, which obviously has to be told how to solve the problem. Because the problems are so large, the surface space is so large, they usually relax the problem to get a heuristic measure and solve the problem that way. I mean, some of them are very good, quite complicated, but very good. So as an alternative to that, we're using CSPs for planning. And in order to encode a planning problem as a CSP, it's essentially 4 steps. We define the variables, set up the constraints to describe the initial state and the goal state. We need to encode the actions that will take us from the state, so we have to switches between states. So we have to encode those as constraints. So the actions in the planning world become constraints in the constraint world. And that's telling us what does change between states. We've also got to tell what doesn't change between states. So we have a load of frame axioms as well. So what we do is we take the propositional PDDL description, we convert it to something called SAS+, which is a multi-valued representation, many fewer variables, each with larger domains of values, which is probably sounding exactly like a CSP. Right? So it's ideal to get a CSP encoding from. I chose to encode the constraints extensionally, and might sound like nuts. I'm sorry if you know what that means. It means essentially you write out all of the possible values, everything. You know, essentially you're just writing out everything that's possible, as compared to like just setting up relations of things. And we implemented the whole thing in Eclipse. So just to recap, start off in PDDL, translate it into SAS+ encoding, convert that into CSP encoding, which is suitable for the Eclipse solver, and press the button, and sometimes wait for hours and hours, and get something of a solution. All right, fabulous. So that's basically, the thing on the right is the CSP version of the thing on the left. That's the initial state across here. Each of the rows is a state. That's the initial state across there. Obviously, I've just shown a couple of 3 variables. That's the goal state, and these are the action variables. So action 1, which has has a domain of 109 possibilities, values, that acts on the initial state to give us the second state. Action 2 operates on that to give us the third state, and so on. So what we need to do is find values for all of these, which gives us values for all of these. These are just placeholders, these are just labels, so action 1 could be action 85, So we'll have a list of numbers down here, which will correspond to actions in this world, and as we read it down from the top, it will say things like board truck, or walk driver, board truck, drive truck, load truck, drive truck, come with truck collecting. So essentially, that will be the solution, the CSP solution, which translated into a solution for that planning problem. So why would we bother doing this? Converting it into a CSP as opposed to a planning problem. We've got standard CSP solvers. We can use the propagation and pruning machinery. Essentially, it's free money. Like it's kind of free money. It's a declarative paradigm. Ideally, you state the problem, set it to go, and it can infer quite a bit, you hope, and rely much less on blind search. So that would be great if that was the be all and end all, but it's not. So this is us just setting up the variables with their domains. If we apply the constraints and check the consistency, what we're getting, if you like, for nothing is the domains of these variables are reduced. So as a result of these fixed values here and the fixed values here, we're propagating and we're able to reduce the domains of these variables across here and here. So if this was quite a smaller problem, this would be pushing up into this, and we could potentially infer a solution without any search or very little search, very little backtracking. So the downside is, as we've just seen, sort of, the larger problem means a larger search space. Because the two ends are further apart, the propagation, he says, it's never going to meet anywhere in the middle, so we're losing, we're not getting a very good hit from this. The impact is reduced, much less inference. And the other thing is, we're losing the planning problem structure. If you look at the if you look at that, for CSP people that might look fabulous, but like, what is it? It's just a series of numbers, right? It doesn't look like a planning problem, doesn't look like anything really. So you kind of like you can't really capitalize on the fact that the truck's near the driver, or the driver, the truck's near the bike, or whatever. Right? So you're losing all that structure as well. So we get to the CSP heuristic, planning specific CSP heuristic. So what we do is we use the problem structure to order the goals. We select each of the ordered goals in turn. We find a point in that matrix, the earliest point where that goal is possible. What that does is, if you imagine, we're taking this goal value, we come up, we find the earliest point where it's possible. That then sort of sticks in a stepping stone, if you like, a bound, a horizon. And then we can push up from that, push down from, in the first case, the initial state, and we're getting what we want, hopefully we are. Again, essentially decreases the horizon and gives us more inference, or gives us what we were wanting in the first place. So let's just have a look at that, how that's going to work. So that's the CSP. This is what we get for nothing by doing nothing. What would happen normally is we'd set it running, and for example, starts up here, picks a value for this one, let's go for 0, picks values for all of the rest, gets down to here, finds it can't do anything, backtracks to the next one here, does the same again, essentially yada yada yada, thrashes about until eventually backtracks all the way up here, picks the correct one, comes down, and it might do the same again here. Thrashing the whole time, all the way back up, and literally could take days or longer. So by doing what we're doing, we're taking the first order goal in this example is this one here, variable 3. So we want 0. 0 is the goal. Oh, no. Keep it fit. What's that? I don't know. So we want a 0. We move up here and find the first place we can put a 0, and it's here. Actually, it's not, it's here, but the inference is so weak that when we put it in here, it finds out it can't do it. Backtracks over it, pops it in here, which is appropriate, it is actually okay. The action that achieved that, one of two possibles, we get a set of suggested actions. Sorry, but that's not what we're doing. Okay. I won't touch it. So we move up. We have a set of suggested actions that give us the value 0. We pick the first one. It happens to be action 68, which is an unload the package from the truck at S2, which achieves this goal, one of the goals. Then all we really have to do, incidentally, the solver infers this action for us for nothing, because essentially it's saying you're unloading a truck, you're unloading a package. That package wasn't in the truck before. The package was somewhere else, so you're going to have to have loaded it. The only place you can have loaded it is here. So this is the problem that we need to solve now. This little CSP, which is bounded by this and this. We recursively do the same thing. The preconditions of this action become the new goals, and we backfill and find supports for this goal-achieving action. So what that gives us is a little subplan which achieves one of the goals. We drop back down to the top level, pick the next order of goals, and repeat. So we're building up a plan to achieve the whole thing by achieving lots of little things. And that's us. So we applied that to a series of planning problems, planning benchmarks. There's a thing called the International Planning Competition, which is actually from like really kind of quite small roots. It's grown, it's massive now. I think people vie for prizes and all that, and it's a worldwide thing. So this is where these benchmarks are from. But I mean, they're quite small problems, they're not huge, but just to give us an idea of what's happening. So the first three, like the standard search is actually beating the heuristic. The heuristic is an overhead. The problems are so small that essentially they're solved. So the heuristic, the time it takes to run the heuristic is an overhead. In all but 2 of the rest of them, it's faster, sometimes considerably so. You might be thinking, oh yeah, what's going on here? Well, these are forms of nonlinear problem. Because this is goal directed, essentially it's picking a goal, finding a set of actions that will achieve that goal. If there's anything unusual about that goal, if something has to happen before that's not kind of super obvious, this algorithm will never do it. Right? So it's going to pick a goal achieving action, it's going to find out how do I support that, do it. It's going to come down maybe a couple of further actions, and one of those actions won't be achievable because something had to happen somewhere way back in this chain, which would never be done using this algorithm. If you were blind searching, eventually it would. It's a possibility because it's a possibility, because it's there. It doesn't really make any sense sometimes when you're looking at the plan, but it's in the search space, so it's possible. So what happens is the standard search gets to that first. The heuristic gets to a point where it essentially says, right, I've done everything I can do using this algorithm and I can't solve this. So it defaults to standard search, backtracks, defaults to standard search, and that's why we're getting a hit on here. This one took me ages to understand this domain. Essentially, it's an electrical. Sorry, 2 minutes. No, thanks. It's like an electrical switching domain for like high voltage transmission, substations, and transformers and all that. And the plans are really complicated. You have to essentially the problems are. There's a fault on some part of a very complicated interconnected network, and you want to connect as many subscribers without reconnecting a part of it that has a fault on it. So there's a series of switches, and the thing about this is you have to do and undo sometimes the goal state goals. So with this algorithm, you do a goal state goal. If you undo it, you're not going to do it again, following my algorithm. So we drop back into standard search, and eventually, I mean, I figured it would be better to do that than just stop and say, right, I can't do this. So default to the standard search and come up with some solution, albeit a very lengthy one, one that takes a long time. Talking a long time, I'm nearly done yet. Okay, sorry. So just very, very, very quickly looking at the backtracks. Practically no backtracking at all for the heuristic, except in these kind of obvious cases. That's me. Thanks very much, Melissa.
That's good.
So you say you lose the problem structure when you encode the planning problem as a CSV. That's
yeah.
So one way to encode it is using variable and value ordering, as you did to guiding the search using Heuristic. Or you could also try encoding the structure as constraints.
Yeah.
Did you try any of that?
I didn't understand what you mean. So you're saying essentially encode the goal ordering, or that's what it would be, right?
For example, you can say if there aren't any constraints saying this individual driver has to be on that individual truck, you can say you can permit two trucks, so it doesn't matter which truck it is. So you can just strict ordering on the truck.
Yeah, you mean and put it.
Oh, write a constraint for it.
Right, but like automatically, so, yeah.
Well, in your planning to CSV transformer, it has the structure at hand, so it can possibly generate some constraints.
Okay, yeah, I mean, as I say, I understand, but I don't know. So essentially, you'd be saying something at that stage like, don't put driver 1, always associate driver 1 with truck 1.
Yes.
Right, and it might be just like pig-headed or whatever the phrase is of me, but I didn't want to do anything like that. At this stage, I didn't want to use learning or anything hand-coded. I mean, there are some classic CSP planners from a few years ago where essentially it's one problem, they hand-coded it, and it's amazing. Mm-hmm. Yeah, right. I mean, it's human solving, right?
But if you could do it in general for
it's brilliant. You're right. I mean, because for problems with symmetry, wipe it out. It'll be done in a second. You're taking out all those potential wrong or irrelevant.
But you do the same with your heuristic now. You do something very similar with your heuristic.
Yeah, we do. We're picking the first goal-achieving action. If it doesn't work, we backtrack and pick the next one. What I'm working on now is a couple of things. A meta CSP idea for locking those goals, just essentially lock it all the way down, and it should cut a path, and the cumulative effect of that should be pretty fair as well. The other thing is do a heuristic measure on, for example, a problem like that, and do a heuristic measure of which truck is closest, which driver is closest. You can actually do that, and then you're pretty certain you've got the shortest plan. Thanks.
Karen, Bilal, you can do that. Sorry.
So, have you thought about running, or do you run a pre-processing on your CSP before you start searching for a solution?
You mean some sort of consistency checking or
signal
forward?
to noise consistency or signal to syntax, something like that?
Not really, not as a kind of processing stage. I mean, you think that's
it might be worth trying, because one thing I think when solving CSP is not ones. If you run a preprocessor first, it's amazing actually sometimes what you can actually incur.
Right.
And it might be that you actually see from that something that will help your planner.
Oh, okay.
So I suggest giving it a go. It might not work in your domain, but it might be.
It probably would work. I mean, it's like everything. It'll probably, hot butter through knife on some of these problems and do nothing on some others. But that's good one. Good one. Thank you. That's all.
Do you have any further questions?
Coming closer to our area.
No problem.
Just like, it looks like the heuristic is trying to attack the whole problem class of planning problems.
Yes.
Maybe instead, if you could have subclasses of planning problems and tune the heuristic for each subclass and see how it performs.
Again, absolutely brilliant and correct, of course. I'm kind of just at the moment like, what does this thing do? Let's see what it does. And then hopefully, like you say, kind of transportation-based problems. and sort of problem and try to classify what it's really good at and what it's really bad at.
I think I'll end the questions there. Can we thank your speaker again?
So, I'm Bilal from University of Anderson. Today I'm going to go talk on automatic constraint model. So first of all, what is constraint solving? As you probably heard from other lectures, constraint problem is part of solving a wide range of problems, such as optimization problems and time tethering. A constraint satisfaction problem consists of a set of variables with associated domains, such as a set of ints, and constraints with space restrictions on these values, such that, let's say, x can't be 1. So a constraint model is a description of a given problem in terms of CSP. Since there are typically many different models for a given problem, non-experts might have difficulty formulating constraint models. Our approach to solving this difficulty is to allow the user to write high-level specifications in a language lesson, which I'll discuss later, into these constraint models, which allows the user to use high-level notation such as relation sets or model sets and so on. And it provides abstraction, meaning they don't have to worry about how to represent their high-level concepts in terms of the lower ones, while still retaining the efficiency of constraint sets. So Essence is a high-level specification language using notation such as function, relation, partitions, as I said earlier. And it also provides nested types, which have a set of sets, or model sets of partitions, and so on. As a motivating example of describing how descriptive Essence is, I'll show how the social golfers can be specified in Essence. So a social golfers problem is where you have a number of golfers, they want to golf together in groups of size G, and they want to play again for W weeks, such that no two golfers play together all at once. So for each week, we have a set of golfers, so we can partition them. This can be because Essence has partitions onto the weeks. You could use a secret or a list and so on, but since other than actually matter, you could just use a model set, and you would have a symmetry there. So the problem is basically finding model set partitions. So since the golfers are interchangeable, in Essence, so the problem we parameterize, so you give the size of the golfer the size of the thing you want. So this is a class of problems, which means since the model can be defined once into the lower thing and solved multiple times for many different instances of parameters. Since the golfers are interchangeable, we can just order them however we want, which means we can break symmetry and make them more efficient. And for finding the schedule, it's basically that the English description, we want to find a multi-set of size W of a partition. A regular partition means that each part of the partition have the same size. So for association constraint, basically that for each pair of distinct weeks, the intersection of any pair gives most one golfer, meaning that no golfer plays more than once to any other golfer. So that's the complete Essence specification of this, which is reasonably short and matches the English one quite well. It only has one variable and one nested constraint. So the overview of the whole tuition. So the user only interacts with conjure at the top, and Toolchain, our past user, does all the refinement, translation, and translation back to it, and gives the decision back to the user in terms of the specification. So the user gives the conjure in terms of S specification, which is defined once. This is important when we're solving a class of problems with multiple parameters, because the model doesn't have to create multiple times. Code then defines all given parameters into a subset of Essence called Essence Prime, which is a solving independent language. Cyber then takes S prime, finds the optimizations on it, such as an empty common start set in the nation, and converts it to minion inputs. What minion it solves the problem, and Cyber does the reverse process, converting the solution back to S prime. Conj then takes the S prime solution back to essence, and which shows the solution to the problem to the user in terms of the business specification. So, in more detail, so Conj is a tool that generates models from the problem specification. That will pass high efficient models, and minion is ready for this shape solver. So, Conj can generate multiple models. This is the opportunity because then we can pick a selection of models, like either binary picking or using some heuristics, such as a small heuristic represented with each deformation stage, picks the rules that will be applied to it, which is result in the smallest model, which works very well for some problems because you have less things solved. So, in conclusion, automating the constraint model makes CP more successful because it allows you to write high-level specifications while maintaining high performance of CP solvers, and it also allows you to use necessary other notations such as functions, relations, and so on. And it means that no space needed to model the problem or set a good model and to get solution back to the business problem. But way too fast.
Well, thank you, Bilal. Time for questions now?
Yeah, I think that's not way too fast.
Any questions? So, unfortunately, I know all about this work because so I don't actually have any questions. Kevin.
So, what challenges are you facing currently?
We're doing some more interesting heuristics because small scale works for quite a few models, but you could find it better. Like we could do heuristics based on how long it takes a minion, so we can base on that. We can base it on how many variables you have, how big this model is, and various other things we're investigating.
Okay. So what's your PhD project?
Oh,
in this context.
Oh, it's a model selection. So picking good models after the last common basic models that Conj can generate.
So Conj can generate a wide range of models.
Yes.
Oh, I know that. Okay. Okay. If there's no more questions, should we thank our speaker again?
I'd just like to thank you all for coming and for inviting speakers to such a great job with their lectures and with their discussion sessions as well. And for chairs of all the sessions, because I think we really had excellent chairs and they all did their best to keep the discussion going. So I hope you all have a safe journey home. If you're looking for ideas where to go sightseeing for the weekend, come to me and ask. And have a nice weekend all.
Thank you very much to you and Jonathan for bringing it all together.
Jonathan,
here.
yeah.
Thanks,
Jonathan.
Thank you.
Yeah, that was good to meet you. Yeah,